Let's look first at scenario 1, the case where we have a higher degree on the bottom. Right here we have the rational function y equals x minus 3 over x squared minus 5x plus 6. Let's just look at the graph. So if we look at the graph as x approaches infinity, notice that f of x is approaching 0. So as x approaches infinity, f of x approaches 0. And if we look from the left, as x approaches negative infinity, f of x is still approaching 0. Now, if we want to use the horizontal asymptote trick, well, now if we look up here at our rational function and we cross out any of the terms with lower powers, we're left with just x over x squared. So this function is approximately x over x squared when we're going towards positive or negative infinity. Then, if we simplify this, it's going to be 1 over x. So as x approaches infinity, we can bring down our simplified version 1 over x, and let's go ahead and substitute infinity. So notice that we get 1 over infinity, and as we learned over here in our example that we went through, if I have a number over infinity, the horizontal asymptote is y equals 0. So we can just say that this equals 0. Likewise, we can do that as x approaches negative infinity. So 1 over x is going to equal 1 over negative infinity, which is also 0. So as x approaches negative infinity, the limit to the y value is 0. And as x approaches positive infinity, the limit to the y value is also 0. There is a horizontal asymptote at y equals 0. Now it's time for you to get some practice finding the horizontal asymptote when the degree of the denominator is 1 degree higher than the degree of the numerator. So for you, try it 1, please pause your video, work through the example to find the horizontal asymptote. When you're finished, please unpause the video and see if your solution matches with mine. So here's my solution. I went ahead and graphed it so you could get a visual of it. But notice, as x is moving towards positive infinity, that we can see on the graph that the function's approaching 0. As x moves towards negative infinity, you can see the function approaching 0. If we go ahead and use the horizontal asymptote trick, notice that the highest term on the top is x squared and the highest term on the bottom is x cubed. So y then is approximately x squared over x cubed, which simplifies to 1 over x. If we could plug in infinity, we'd have 1 over infinity, which equals 0, as we learned earlier. We have the same argument on the bottom here. As x approaches negative infinity, we end up with 1 over negative infinity, which is still just 0 that it's approaching. So we can say that the limit to the y value as x approaches negative infinity is 0. Likewise, as x approaches positive infinity, the limit to the y value is 0. Lastly, there is a horizontal asymptote at y equals 0. Now let's look at scenario 2, where we have the same degree on the top and on the bottom. Here we have a rational function y equals 4x minus 1 over 2x minus 1. Just looking at the graph, as x approaches infinity, notice that the y values are approaching 2. So as x approaches infinity, f of x approaches 2. And then as x approaches negative infinity, notice that f of x is approaching 2 on that side as well. So we have f of x approaching 2. To use the horizontal asymptote trick, we can cross out the minus 1 on top and bottom here, and we're left with 4x over 2x as an approximation at positive and negative infinity here. And then we can simplify that. And that's going to equal 2. So we don't even have an x left over to plug in a very large positive or a very large negative number. So our asymptote is just 2. So as x approaches negative infinity, the limit to the y value is 2. As x approaches positive infinity, the limit to the y value is 2. There is a horizontal asymptote at y equals 2. So for you, try it too. Please pause the video, work through the example to find the horizontal asymptote. Once you are finished, please unpause the video and see if your solution matches with mine. So here's my solution. I went ahead and graphed it for you. Notice as x approaches infinity that the y values are approaching 0.5. And as x approaches negative infinity, the y values are also approaching 0.5. If we want to use the horizontal asymptote trick, we're going to cross out the 2, the minus x, and minus 1. So we end up with 5x cubed over 10x cubed as an approximation of our function at plus or minus infinity. When we simplify it, we're left with 5 over 10, which equals 1/2, which is 0.5. So, and we have the same argument as x approaches negative infinity. So as x approaches negative infinity, the limit to the y value is 0.5. As x approaches positive infinity, the limit to the y value is 0.5. There is a horizontal asymptote at y equals 0.5. Something that I wanted to bring up is that it is possible to cross a horizontal asymptote. I know that you've learned that it's not possible to cross a vertical asymptote, and that's because they're asymptotes for different reasons. A vertical asymptote is a vertical asymptote because it's a discontinuity. It's a place in the graph where the function's undefined. But a horizontal asymptote has to do with the end behavior. So the horizontal asymptote is going to be valid as you're going to positive or negative infinity. If you're closer to the y-axis, it is possible to cross that because you're not close to positive or negative infinity. Now let's look at the third scenario, where we have 1 degree higher on top. I have here the rational function y equals x squared minus 2 over x minus 1. If you notice the graph here, as x goes towards positive infinity, notice that f of x, or the y values, are increasing without bound. So we can say that f of x is approaching infinity. And as I move towards the left, as x approaches negative infinity, notice that the function values are decreasing without bound. So as x approaches negative infinity, f of x approaches negative infinity. If we look up at our rational function here and we use our horizontal asymptote trick, this becomes approximately x squared over x. If I simplify that, I get just x. And as I look to see, and if I look to see what happens as x approaches infinity, well, I have x squared over x equals x, which equals infinity. And you can see that on the graph, like we looked at a second ago, f of x is approaching infinity. And then I can do the same thing with negative infinity. We have x squared over x equals x. When we plug in negative infinity, it just equals negative infinity. And we saw that when we analyzed the graph. So as x approaches negative infinity, the limit to the y value is negative infinity. As x approaches positive infinity, the limit to the y value is positive infinity, or we can just write infinity. There is an oblique or slant asymptote at, we actually need to find out where that is. So the way that we can do that is we can use synthetic division. If you wanted to use long division, you could, but synthetic is faster. So we can use synthetic division and take x squared minus 2 and divide by x minus 1. So we'll do that over here. So if you remember with synthetic division, the 0 that we have on the bottom is 1. You take that 0, 1, and you divide it into x squared minus 2. So let me just do a side note up here. X squared minus 2, that equals x squared plus 0x minus 2. So over here, we're going to have, for synthetic division, we put the coefficients in there. So the first coefficient is the one for x squared, which is 1. And then for 0x, we have 0. And then we have minus 2. And then we just do a little bar down here. We always start out, you always add vertically, add or subtract vertically, and then you multiply across. So 1 plus 0 is 1. You just bring the 1 down. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. And then negative 2 plus 1 is negative 1. And then you just go in and you can plug back in the variables. So this is always just going to be the remainder if there is one. So this is a remainder. And if we're looking at the behavior towards infinity, that remainder is not going to matter. So we're not even going to use the remainder. And then the next number is going to be the constant. And then the next number is going to be an x. So we have a 1 in front of an x here. And then if we had more moving left, we would just put higher powers of x. So what this actually equals is x plus 1, right? You have 1 times x, or 1x plus 1 right there. So there is an oblique asymptote at y equals x plus 1. And that's actually, you can see the graph right here. This is y equals x plus 1, the asymptote. Now it's time for you to get some practice finding the asymptote when the degree of the numerator is 1 degree higher than the degree of the denominator. I would like you to please pause your video and work out this you try it problem. Once you are finished finding your asymptote, please unpause your video and check your solution with mine. So here's my solution. Notice that I went ahead and graphed it for you. You can see as x moves towards positive infinity, as it's moving to the right, the function is decreasing without bound. So it's approaching negative infinity. Notice as x moves to the left that the function values are increasing without bound, so they're moving towards positive infinity. And you can see that right here. If you use the horizontal asymptote trick, we get rid of all the terms that have lower powers, and so we're just left with negative x cubed over 2x squared. When you simplify that, that's going to give you negative x over 2. Now, as x approaches positive infinity, if you plug an infinity in there, you're going to have negative infinity over 2, which simplifies to negative infinity. As x moves towards negative infinity, then you plug in a negative infinity, you have negative times negative, which gives you positive infinity over 2, which just simplifies to positive infinity. And that goes along with what we saw when we just analyzed the graph. So as x approaches negative infinity, the limit to the y value is negative infinity. As x approaches positive infinity, the limit to the y value is positive infinity. There is an oblique asymptote at y equals negative 1/2 x plus 2. Now again, you can use division to find that. Now I can't use synthetic division here because synthetic division works when you only have a power of 1. So we'll have to use long division. I guess I can go ahead and do that here. So we have negative x cubed plus 2x squared plus 0x plus 0x. We need that placeholder in there. Plus 2. That's divided by 2x squared plus 3. So we have 2x squared plus 0x plus 3. All right, so first we're going to take 2x squared and divide it into negative x cubed. If you need to do side work for that, you can. So that means we're taking negative x cubed. I'm just going to do it over here. And we're dividing it by 2x squared. Well, I've got a little hidden 1 up here, or it's just not written. So this is a negative 1 up here. So we have negative 1. And then on the bottom we have 2. And then x cubed divided by x squared. The x squareds cancel and you're left with just 1x on top. Or you could just put it on the side right here. So this is right here, negative 1/2 x. And then what you do is you multiply it back across each of the terms. So I have negative 1/2 x times 2x squared is going to be negative x cubed, because the 1/2 cancels with the 2. And whenever you're doing this long division here, you always change the sign when you multiply it. So this becomes a positive. And then I have negative 1/2 x times 0x. That's just going to be 0x squared. So we have plus 0x squared, or minus. It doesn't really matter when it's 0. And then we have negative 1/2 x times 3. That's negative 3/2 x. It's going to change to a positive. So we have positive 3 3/2 x so we have positive 3/2 x, and then we can just simplify it. So the x cubes will cancel, and then we can bring down the 2x squared, and then plus 0 plus 3/2 is just 3/2, so we have 3/2 x, and then plus 2. And then we're going to take 2x squared. So you always take the first term and divide it in the first term. So 2x squared into 2x squared is 1. And then we multiply it back. 1 times 2x squared is 2x squared, but we subtract it. And then 1 times 0x is just 0x. And then 1 times 3 is just 3. So, but it's going to become a negative 3. So these are going to cancel here, the 2x squareds. And we have 3 halves x minus 1. So this is a smaller power or a lower power than what we have over here. This is an x to the 1. This is x squared. So this is actually our remainder right here. This is the remainder. And as I mentioned in the last example, when you're going towards positive or negative infinity, the remainder is not going to have much impact at all. So we don't even include it when we write the equation for the asymptote. So up here you see it, negative 1/2 x plus 1. That's our oblique asymptote. Y equals negative 1/2 x plus 1. So just as with a horizontal asymptote, you can cross the asymptote when you're closer to the y-axis. That's also true for oblique asymptotes because, again, they're not discontinuities like vertical asymptotes are. They're just describing what happens towards positive or negative infinity. So here's an example for y equals x cubed plus 2 over x squared minus 9. For this rational function, the function actually crosses the oblique asymptote. Well, that brings us to the end of our video. I will see you next time.